So when you connect those two inverters together, you need to use some interconnects. And those interconnects will also have wire capacitance. So you have this CW. This is what you loop to the node side. This is node. But from this node, you can also look into the first stage. You will have some intrinsic capacitance. Or this node is extrinsic to the first inverter. So what is intrinsic here? This is the drain of the Q1 and Q2, those two transistors, because this NMOS, this is source, and this is drain. For the PMOS, this is drain, this is source. So the drain to the body, and this is the body contact. As shown in the previous slide, this drain to body will have this junction capacitance, this pin junction capacitance. So you have this CDB, drain to body. And you have this for Q1 and Q2. So you have CDB1 and CDB2. So you have those two capacitance here. And also, this node is a drain, and then your input is gate. So this overlap from drain to gate. So let's say CGD is overlap capacitance. This is the COV. That is the capacitance here. The gate to drain. You have this overlap. You have this overlap capacitance, COV. So that will also contribute to this node. So you have the CGD for the Q1 and CGD for the Q2. So you have those capacitance as well. So in total, you have, let's say, 1, 2, 3, 4, 5, 6, 7. 7 capacitance contribute to this node. So if you draw the equivalent circuit eventually, here, this inverter is driving this node capacitance CL, which is the sum of all the capacitance components here. You have all the capacitance attached to this output node. That will be your total CL. So here we will skip the details, and I don't require this in this class, how to calculate the detailed capacitance. But you need to understand the contribution to this CL is coming from the second stage, which is an external extrinsic node, and also it's coming from the first stage, that is intrinsic to this output node. So I will skip the details, how to add them up. So any questions? So those capacitance become your load. All right, so let's look at one example. So in this example, we are given like those parameters like the mu n, mu p for this CMOS inverter, and the threshold for the CMOS inverter, and power supply VDD, and W over L n and W over L p are given. So here it asks to find the TPHL and the TPLH and TP. So here it has a hint that the C total is this number. But this C total actually has two components. So basically here we add everything up, will be this 6.5 femtofarad. So let's use average current method. So in the homework or in the exam, I will tell you which method to use. If I ask you to use average current, then you will use average current. So here let's use average current. So the average current, of course, you will write down the equation for the TPHL from average current. That is C and CL, and then VDD, and half I average. So then the question is, what is the I average? So I average is the I initial and I final. So what is I initial? I initial for the TPHL, initially your VDD, sorry, your VDS is VDD, and finally it dropped to half VDD. And we discussed this is saturation and this is trial. So you just need to find those two currents, the saturation current and trial current for this NMOS transistor. This TPHL is NMOS cooling down. So you can use the equations we have. For example, here, let's say initially, let's plug in the saturation current. And this is for NMOS. Let's do it. So you will have the VGS is VDD and minus VTN squared. So this is the saturation current. And you can plug in all the parameters here. You'll get 800 microamp. And then the final current is a trial current. And you know the trial current equation is like this. VGS minus VGS. VGS is VDD. And the times, sorry, there's the VD times VDS. So what is VDS at this moment? Here it says it's half VDD. And then minus the half VDD, which is VDS squared. So you have this equation for the final current. And you can plug in the parameters. You will get 690 microamp. So then the I average will be the average of those two. That will give you 740 microamp. So then you can plug in this I average to this equation with this CL 6.25 femtofarad, VDD 2.5 volts. So you will get eventually the TPHL will be I think I messed up here. So it's not this one. The number is wrong. So the number is wrong. So here the equations are correct. But the numbers is wrong after you plug in the numbers. So this one will give you 3, 4, 5. And the other one is 2, 9, 7. So the average is, let's say, 321. And the TPHL will give you 24.6 picoseconds. So just plug in the numbers and you can do the calculations by yourself. So any questions? So that is the approach. Any questions? So similarly, you can get the TPLH. The only difference here is that you need to plug in all the PMOS parameters, like mu n become mu p, W over Ln becomes W over Lp, and the Vtn become Vtp. So if you do that, then you will get the TPLH. Because PMOS is for low to high. PMOS is pulling up from low to high. So if you do that, you will get 31.5 picoseconds. So this is unmatched if you look at those two numbers. So this NMOS and PMOS are unmatched. So if they are matched, you will get the same number. But in this example, they are not matched. So here you see that NMOS is stronger because high to low. This is because NMOS is pulling down and PMOS is pulling up. So you see the NMOS is stronger than the PMOS. So from high to low transition is faster than the low to high in this example. But on average, you get TP, which is the average of those two. That will give you 28 picoseconds if you average those two. So any questions in this example? So this is to use the average current. And then let's look at the CMOS inverter gate sizing. So here we are looking at increase the size of first inverter by a factor of S. So if you increase the size by S, that means W over L. The first inverter is increased to W over L S times W over L1. And then W over L2, which is the PMOS here, also increased to S times. So we make them larger. Let's say S is larger than 1. However, the Q3 and Q4, let's say unchanged. So we size up the first inverter by a factor of S. And you know all the capacitance here associated with the inverter 1. That means those 4. Here is capacitance, let's say 1, 1, 2, 3, 4. So those 4 capacitance will also increase by S, because those capacitance proportional to the width of those transistors. If you increase the width by S, then those capacitance will increase by S as well. So here we have two, let's say the same node has 2 components. One is intrinsic or internal. The other is extrinsic or external. So internal means internal to first stage inverter. So that includes this 1, 2, 3, 4. That includes C1 to C4. And this external is, let's say, C5, 6, 7. So external means outside the first inverter. That is C5 to C7. So if you increase the size by a factor of S of the first inverter, so then the internal capacitance will increase by S. But external one will be unchanged, because here we assume Q3 and Q4 unchanged. And then for the equivalent resistance, okay. So let's say the Rn and Rp. So here we use RC equivalence. So the TP will be 0.69 RC. But if you increase the size by S, your equivalent resistance will reduce by S, because the resistance is proportional to 1 over W over L. If your W over L increase, then the resistance will reduce by this factor. So here we are interested in what is the new TP. The old TP, and let's say before size up, this is your TP, 0.69 R equivalent and times C. And after size up, so we will plug in the new R, which is this one, because your resistance reduced by S. And the C will be this one. This is your new C. Let's say this is a new R. This is a new C. So you will have a new R and a new C. So if you look at those two, when you plug in those two, and then you multiply this one with this one, so the S here will cancel out. So you still get this one. But the second term here will have 1 over S factor here. So that means what? So it means after you size up, for the first stage, nothing changed. When you size up, capacitance go up, resistance go down. So RC, one up, one down by S factor. So they cancel each other. So the delay for the first stage, the internal delay, unchanged. But the external delay gets reduced by the 1 over S. So this is internal delay, let's say internal. This external. So the internal delay, no change. The conclusion here is that no change. But the external delay reduced by 1 over S. So any questions here? So we can look at one example for this sizing. So here, let's say this intrinsic or internal and external cap. So this means C1 to C4, the sum is this one. C5 to C7, sum is this one. So if it asks what W over L needs to be increased to reduce the extrinsic external part of the TP by a factor of 2. That means you want to reduce the external delay, this part, by a factor of 2. Then of course your S factor will be 2. Then your W over L will increase by 2. And estimate the resulting TP. So your TP has two components. you can, let's say, your TP has two components, internal and external. So what is internal TP? So initially, before size up, this is related to the previous example. So here with TP we get 28 picoseconds. So before size up, TP is 28 picoseconds. But you want to look at internal versus external. Within this 28, how much come from the internal? How much come from the external? So since this is proportional to the cap, internal and external, so you can have the total cap, which is internal plus external, and say internal times TP. So this will give you internal delay. It's just a ratio of this 2.9 over the total is 6.25, or let's say 2.9 plus is 3.35 times 28, which will give you like 13 picoseconds. So this is internal. This is internal delay. And the external delay will be external times say external plus say internal times TP. That will be will be 15 picoseconds. So here, when you size up, after size up, by S equals 2. So our conclusion here, internal no change, external reduced by 1 over S. So that means this internal delay, no change. No change. And this external one reduced by 2. That means it becomes 7.5 picoseconds. So the new delay will be this 13 plus this 7.5. Then it will become 20.5 picoseconds. So the old delay